Welcome to the Late Lab. It's wonderful to have you here. Before we wander too far into the deep interior of matter, I'd love to know where you're listening from tonight. Maybe you're tucked beneath a blanket, maybe you're on the last train home, maybe you're in a quiet room with the lights low and the world finally giving you a little space. Wherever this finds you, I hope you're comfortable, settled, and ready to let your thoughts drift very gently inward. If you enjoy these calm journeys through science, a like and subscribe helps this little laboratory keep glowing quietly in the dark. And if you're already here often, thank you, truly. It means a great deal that you choose to spend your quiet hours exploring the universe with me. Tonight, we're going to travel into one of the strangest facts in modern physics. There are particles inside ordinary matter that, as far as we know, can never be found on their own. Not because they are shy, although that would be a charmingly simple explanation, but because the force that holds them behaves in a deeply unusual way. These particles are called quarks. They sit inside protons and neutrons, helping to build the atoms that make stars, planets, oceans, teacups, biscuits, and, somewhat inconveniently, the person currently wondering whether a biscuit would improve this explanation. But unlike electrons, photons, or many other particles, quarks appear to be permanently confined. You can pull at them, collide particles at enormous energies, and try to separate them with machines built by some of the most advanced research organizations on Earth. Yet a single isolated quark never simply drifts away into the detector. Instead, nature does something far stranger. As the energy between quarks increases, the vacuum itself can produce new particles, and the attempted separation gives birth to more bound matter rather than freeing the original quark. It is a little like trying to snap a piece of elastic, only to discover that the universe quietly ties new knots before you can finish the job. So let's begin, shall we? What is a quark? Why can it never exist alone? And what does confinement reveal about the hidden force holding ordinary matter together? When you look around a room, it is very easy to believe that matter is simple. A table feels firm, a wall seems still. A cup rests quietly in your hand as if it is made from something solid all the way down. The world around us gives the impression of being continuous, dependable, and mostly uninterested in doing anything dramatic, which is kind of it, really. A table does not usually behave like a particle accelerator, and for that we should probably be grateful. But the stillness of ordinary matter is a kind of disguise. Beneath the smooth surfaces of the everyday world, matter is built in layers. The wood of a table, the glass of a window, the water in a cup, and the cells in your body are made from atoms. Each atom has a tiny central nucleus, surrounded by electrons, held in place not like little planets orbiting a sun, but by the rules of quantum mechanics. Inside the nucleus are protons and neutrons, and inside those protons and neutrons are quarks. This is where the story becomes much stranger. An electron can exist on its own. A photon, the particle of light, can travel freely across space for billions of years. Neutrinos stream through planets almost as if the planets are barely there. But quarks are different. As far as every experiment has shown, a quark cannot simply be found alone. A quark is not fictional. It is not just a mathematical convenience. Quarks are fundamental particles in the standard model of particle physics, the great framework that describes the known elementary particles and the forces acting between them, apart from gravity. The standard model includes particles such as electrons, neutrinos, photons, quarks, and the force-carrying particles that govern their interactions. It is one of the most successful scientific theories ever built, tested again and again in particle accelerators and detectors across the world. And yet, within this very successful theory, quarks have a peculiar status. They are real enough to explain the structure of protons and neutrons. They are real enough to leave measurable traces in high-energy collisions. They are real enough that without them, the pattern of known particles would make far less sense. but they are never seen drifting alone through a detector, like a tiny charged bead that has escaped from a proton. Instead, quarks are found inside composite particles called hadrons. A hadron is any particle made from quarks and held together by the strong interaction. The proton is a hadron. The neutron is a hadron. More exotic particles created briefly in particle accelerators or cosmic ray collisions are hadrons too. Some hadrons are called baryons, such as protons and neutrons. Others are called mesons, made from a quark and an antiquark. But in every ordinary case, the quarks remain bound inside a larger particle. This strange imprisonment is called confinement. Confinement means that particles carrying a special kind of strong force charge, known as color charge, are not observed as isolated free particles. Quarks carry color charge. Gluons, the particles associated with the strong force, also carry color charge. But the particles that appear freely in nature must be color neutral overall. A proton, for example, contains 3 quarks arranged so that their color charges combine into a neutral whole. A neutron does the same. Mesons combine color with anticolor. The individual quark, however, remains hidden inside the partnership. This is not because our machines are too clumsy in some simple sense. Physicists have used enormously powerful accelerators to smash particles together at tremendous energies. Facilities such as the Stanford Linear Accelerator Center, Fermilab, Brookhaven National Laboratory, and the European Organization for Nuclear Research have explored matter at distances far smaller than an atomic nucleus. These experiments have revealed the behavior of quarks with extraordinary precision, but they have not found a single loose quark wandering away on its own. The reason lies in the strong interaction. The strong interaction is one of the fundamental forces of nature. It is the force ultimately responsible for binding quarks together inside protons and neutrons. It also explains, in a related but more indirect way, why protons and neutrons can bind together inside atomic nuclei. The deeper theory of the strong interaction is called quantum chromodynamics. That name sounds wonderfully dramatic, as if someone gave a rainbow a doctorate, but it has a precise meaning. Quantum chromodynamics is the quantum field theory of color charge, quarks, and gluons. Its behavior is unlike anything familiar from everyday life. With forces such as electromagnetism, particles with charge can often be separated more easily as they move farther apart. The force weakens with distance. But the strong interaction between quarks does not behave in that simple way. When quarks are pulled apart, the energy in the strong field between them increases. If enough energy is added, nature does not allow one quark to break free. Instead, that energy can create a new quark and antiquark pair. The result is not an isolated quark, but new hadrons. So the deeper you look into ordinary matter, the more unusual its foundations become. The stable objects around us depend on particles that cannot be individually removed from the tiny structures they help create. The proton in every hydrogen atom, the neutrons and protons in heavier nuclei, and much of the mass of the familiar world all depend on this hidden strong force. Matter is not calm because nothing is happening inside it. It is calm because what is happening obeys rules so strict, so deep and so strange that even the smallest particles are not always free to stand alone. For a long time, the atom was where the search seemed to end. The word itself comes from an old idea, something that cannot be cut. Long before modern laboratories, long before particle accelerators, and long before anyone had a clear picture of the nucleus, philosophers had wondered whether matter could be divided forever. If you cut a piece of wood in half, and then cut that half again, and then kept going in imagination, would there eventually be a smallest piece? Or would the cutting never truly stop? For many centuries, this remained more a philosophical question than an experimental one. But in the early 19th century, John Dalton gave the atomic idea a new scientific form. Dalton proposed that chemical elements were made from tiny indivisible units called atoms, and that different elements had different kinds of atoms. Hydrogen, oxygen, carbon, iron, and all the other elements were not just names for substances. They were built from distinct atomic ingredients that combined in fixed ratios. This helped explain why chemistry had such regular patterns. Water was not a vague mixture of hydrogen and oxygen. It had a definite composition. Carbon dioxide was not simply carbon and oxygen in any loose arrangement. It followed a particular combining rule. Dalton's atomic theory made matter seem wonderfully orderly. The world was not just a continuous soup of stuff. It was built from tiny units, combining and recombining according to rules. At first, these atoms were imagined as solid little particles, rather like miniature billiard balls. That picture was simple, useful, and completely understandable. It was also wrong. The first major crack came from the electron. In 1897, J. Thomson, working at the Cavendish Laboratory in Cambridge, studied mysterious rays produced inside glass tubes, from which much of the air had been removed. These were called cathode rays. Thomson showed that they were streams of tiny negatively charged particles, far smaller than atoms. He had discovered the electron. This was a turning point. If atoms contained electrons, then atoms could not be the final indivisible pieces of matter. They had internal structure. Something smaller was living inside them, which is a mildly rude thing for an indivisible object to do. Thomson imagined the atom as a kind of positively charged sphere with negatively charged electrons embedded inside it. This became known as the plum pudding model, which is a very British name for an atomic theory. In this picture, the atom was still roughly spread out and soft in structure. Positive charge filled the atom, while electrons sat within it like little pieces of fruit in a pudding. But then came Ernest Rutherford. At the University of Manchester, Rutherford and his colleagues Hans Geiger and Ernest Marsden carried out one of the most important experiments in the history of physics. Around 1909, they fired alpha particles at extremely thin gold foil. Alpha particles are positively charged particles emitted by certain radioactive materials, and they were used as tiny probes of atomic structure. Most of the alpha particles passed straight through the gold foil with little change in direction. This made sense if atoms were mostly empty or gently spread out. But a small number bounced back at large angles, as though they had struck something very dense and very small. Rutherford later compared the surprise to firing a shell at tissue paper and seeing it come back. It was not what the plum pudding model predicted. If positive charge was spread smoothly throughout the atom, there should have been no tiny central target strong enough to repel an alpha particle so dramatically. In 1911, Rutherford proposed a new model. The atom, he said, must contain a tiny, dense central nucleus carrying positive charge with electrons outside it. The atom was not a soft pudding after all. It was mostly empty space, with nearly all of its mass concentrated in a centre far smaller than the atom itself. The scale is difficult to picture because it is so extreme. An atom is already very small, typically about a 10/1000th of a metre across. But the nucleus is about 100,000 times smaller in diameter than the atom. If an atom were expanded to the size of a large room, the nucleus would still be only a tiny speck near the centre. The rest would be almost entirely open space, shaped not by hard little walls, but by electric fields and quantum rules. This does not mean matter is flimsy. A table is not easy to walk through, even if atoms are mostly empty space. The solidity of matter comes from electromagnetic forces, quantum mechanics, and the behaviour of electrons in atoms. But Rutherford's discovery revealed something profound. The familiar world is built from structures that are far more spacious and layered than they appear. The nucleus itself became the next mystery. The positively charged particles in the nucleus became known as protons. A proton carries positive electric charge, equal in size and opposite in sign, to the negative charge of the electron. But protons alone could not explain all atomic masses. Many nuclei were heavier than their electric charge suggested. The missing piece was the neutron, discovered by James Chadwick in 1932. The neutron has almost the same mass as the proton but no electric charge. So the modern atom began to take shape. Electrons belong to the surrounding quantum structure of the atom, occupying allowed states rather than neat little planetary orbits. Protons and neutrons occupy the tiny central nucleus. The number of protons determines the chemical element. Hydrogen has 1 proton. Carbon has 6. Oxygen has 8. The number of neutrons can vary, producing different isotopes of the same element. This picture was already far deeper than Dalton's atom. Matter was no longer made of indivisible grains. Atoms contained electrons and nuclei. Nuclei contained protons and neutrons. Each layer answered one question while opening another, and that is where the path turns inward again. Once the nucleus had been revealed, and once protons and neutrons had taken their place at its centre, a new question quietly appeared beneath the old one. Were protons and neutrons truly fundamental? Were they the final pieces of the atomic nucleus? Or were they, like the atom before them, structured objects hiding something smaller inside? The answer would eventually lead to quarks. The atomic nucleus is so small that it is tempting to imagine it as a quiet little centre, sitting peacefully inside the atom. But it really should not be so calm. Inside the nucleus, protons are packed extremely close together. Each proton carries positive electric charge, and positive charges repel other positive charges. This is one of the basic rules of electromagnetism. It is the same broad principle that makes two like poles of magnets resist each other, and the same kind of electrical behaviour that can make a balloon cling to a jumper after a little enthusiastic rubbing, which is probably one of the gentler ways physics announces itself in a living room. The problem is that the repulsion between protons should be enormous at nuclear distances. The classical principle behind this was described by Charles-Augustin de Coulomb in the 18th century. Coulomb's law explains how electric forces act between charged objects. Like charges repel, opposite charges attract, and the force becomes stronger as the distance between the charges becomes smaller. In clear spoken form, the idea is the electric force between two charges grows stronger when the charges are close together, and weaker when they are farther apart. That sounds simple enough, but inside the nucleus, it becomes a serious problem. A nucleus is tiny, usually only a few femtometers across. A femtometer is 1/quadrillionth of a meter. At that scale, protons are crowded together in a space so small that their positive charges should push them violently apart. A helium nucleus contains 2 protons, a carbon nucleus contains 6, an oxygen nucleus contains 8. Heavy nuclei can contain dozens. With all those positive charges packed into such a small region, the nucleus should fly apart almost instantly. And yet it does not. The nuclei inside ordinary matter are not constantly exploding. Carbon atoms remain carbon atoms. Oxygen atoms remain oxygen atoms. The calcium in bones, the iron in blood, and the nitrogen in air all depend on nuclei that hold together long enough to build a stable world. Some nuclei are radioactive and unstable, but many are stable for times far longer than a human life, and some are stable for the age of the universe as far as we can tell. So another force must be at work. This force has to be stronger than the electromagnetic repulsion at extremely short distances. It has to overcome the positive charges of the protons and bind the nucleus together. It also has to be very short-ranged, because we do not feel it reaching across everyday distances. You do not notice the strong nuclear force tugging a spoon across the table. The spoon, one assumes, has enough going on. This binding interaction became known as the strong nuclear force. The strong nuclear force is responsible for holding protons and neutrons together inside atomic nuclei. It is not the same thing as electric attraction, because neutrons have no electric charge. It is not gravity either, because gravity is far too weak at the scale of individual particles. The strong nuclear force is its own kind of interaction, powerful across distances comparable to the size of a nucleus, but rapidly fading outside that tiny range. James Chadwick's discovery of the neutron in 1932 help clarify the picture of the nucleus. Before the neutron was discovered, physicists knew that nuclei had more mass than their positive charge alone could explain. Chadwick showed that the nucleus contained neutral particles with almost the same mass as protons. These neutrons helped explain why different isotopes of the same element could have the same number of protons but different masses. A carbon atom, for example, always has 6 protons. That is what makes it carbon. But it can have different numbers of neutrons. Carbon-12 has 6 neutrons. Carbon-14 has 8 neutrons and is radioactive. The neutron made nuclear structure much more understandable, but it did not remove the deeper mystery. Even if neutrons helped add mass and influence stability, the nucleus still required a binding force. Protons still repelled one another electrically. Neutrons still had to be held in place. The nucleus was not merely a collection of little balls sitting politely in a cluster. It was a dense quantum system, held together by a force unlike the familiar ones. In the 1930s, the Japanese physicist Hideki Yukawa proposed an important idea. He suggested that the nuclear force might be carried by particles in a way that would later become central to particle physics. Yukawa predicted that this force carrier would have a mass between that of the electron and the proton. Particles in this mass range later became known as mesons, from a word meaning middle. The pion, discovered later in cosmic ray studies and accelerator experiments, became closely associated with Yukawa's idea. In the older nuclear picture, protons and neutrons could be imagined as exchanging mesons, and this exchange helped explain the attractive force binding them together inside nuclei. This was a powerful step. It showed that forces could be understood through particle exchange, and it helped connect nuclear physics to the growing world of particle physics. But even this was not the deepest layer. The strong nuclear force that binds protons and neutrons inside nuclei is now understood as a leftover effect of something more fundamental. Protons and neutrons are themselves made of quarks. Those quarks are bound together by gluons through the deeper, strong interaction described by quantum chromodynamics. So there are really 2 levels to the story. At one level, the strong nuclear force binds protons and neutrons into nuclei. At a deeper level, the strong interaction binds quarks into the protons and neutrons themselves. The nucleus is calm then, not because it is simple, but because a hidden force is doing astonishing work at distances far too small to see. Once physicists had learned to look inside the atom and then inside the nucleus, something unexpected began to happen. The world did not become simpler. For a while, the basic cast of matter seemed fairly manageable. There were electrons outside atoms. There were protons and neutrons inside nuclei. There were photons carrying electromagnetic radiation. It was not exactly a small story, but it still felt like one the human mind could place neatly on a shelf. Then the shelf broke. In the middle of the 20th century, physicists began discovering more and more particles. Some appeared in cosmic rays, which are high-energy particles arriving from space and striking atoms in Earth's atmosphere. Others appeared in accelerator experiments, where particles were deliberately smashed together at high speeds. These new arrivals were often unstable, living for tiny fractions of a second before decaying into other particles. They were real, measurable, and extremely inconvenient for anyone hoping nature had only a few ingredients. One of the first shocks came in 1932, when Carl Anderson discovered the positron while studying cosmic rays. The positron is the antimatter partner of the electron. It has the same mass as the electron, but positive electric charge instead of negative electric charge. Paul Dirac's theory had already pointed toward the possibility of antimatter, but Anderson's discovery showed that this strange idea was not just mathematics. Antimatter existed in the real world. This widened the particle landscape dramatically. If the electron had an antimatter partner, perhaps other particles did too. Matter was beginning to look less like a tidy collection of permanent pieces and more like a restless field of possibilities, where energy could briefly become particles, and particles could transform into other particles. The tools of discovery were becoming more powerful as well. Cloud chambers allowed physicists to see the trails left by charged particles moving through supersaturated vapor. Bubble chambers, later developed and widely used in particle physics, let particles leave visible tracks through superheated liquid. These tracks could curve in magnetic fields, split into decay paths, and reveal the charge, mass, and behavior of particles that lived far too briefly to be seen directly. The pictures were beautiful in their own way, like ghostly handwriting from the subatomic world. And what they revealed was a crowd. There were mesons, including pions and kaons. There were baryons, including protons, neutrons, and heavier cousins. There were strange particles, called strange not because physicists had run out of sensible adjectives, though one does sometimes wonder, but because they were produced in one way and decayed in another surprisingly slow way. Their behavior suggested a new property that became known as strangeness. Particle accelerators made the situation even richer. At institutions such as Brookhaven National Laboratory, Lawrence Berkeley National Laboratory, and the European Organization for Nuclear Research, physicists collided particles with increasing energy and watched the debris. Each new generation of experiments seemed to reveal more short-lived resonances and unstable particles. Instead of a few fundamental building blocks, physics seemed to have discovered an entire particle zoo. The phrase was appropriate. There were too many species to ignore, too many patterns to dismiss, and too many names for anyone who enjoyed a peaceful notebook. A crucial distinction began to emerge. Some particles, such as electrons and photons, did not seem to experience the strong interaction in the same way, but many of the newly discovered particles did. These strongly interacting particles became known as hadrons. Hadrons are particles affected by the strong force. They include baryons and mesons. Baryons include the proton and neutron, along with heavier unstable relatives. Mesons include particles such as pions and kaons, which play important roles in nuclear forces and particle decays. Today, we understand hadrons as composite particles made from quarks and held together by gluons. But at the time, the deeper structure was not yet clear. The number of hadrons became suspicious. In science, a long list of objects can mean two very different things. Sometimes it means nature is simply complicated, but sometimes it means that the list is hiding a pattern. The periodic table of elements, for example, once looked like a catalogue of different substances. Then atomic structure revealed why the elements had repeating chemical properties. The pattern pointed to something deeper. The particle zoo began to feel similar. Mesons and baryons did not appear randomly. They could be grouped by electric charge, mass, strangeness, and other properties. Certain particles seemed related to one another, almost as if they belonged to families. The problem was that no one yet knew what those families meant. This was the point where particle physics needed more than discovery. It needed order. The overflowing particle zoo pushed physicists toward classification systems based on symmetry. Symmetry, in physics, is not only about shapes looking pretty when turned around, though that is always pleasant. It is about transformations that leave important features unchanged. When particles can be arranged according to symmetry, the arrangement may reveal hidden rules beneath their behavior. That search for hidden order would lead toward flavor, the eightfold way, and eventually the quark model. The strange crowd of particles was not the end of simplicity. It was the clue that simplicity had moved one layer deeper. The particle zoo was crowded, but it was not completely chaotic. That was the important clue. When physicists looked at the growing list of hadrons, they did not see particles scattered at random across nature, like someone had shaken a box of subatomic confetti and hoped for the best. The particles had properties that could be compared. They had electric charges. They had masses. Some carried a property called strangeness, which helped explain why certain particles were produced readily through the strong interaction, but decayed more slowly through the weak interaction. They also had spins and other quantum characteristics that placed them into groups. The question was whether those groups meant anything. In the early 1960s, Murray Gell-Mann in the United States and Yuval Ne'eman in Israel independently helped organize the known hadrons using symmetry principles. The result became known as the Eightfold Way. The name was borrowed from Buddhism, although the physics itself was less about spiritual enlightenment and more about trying to stop particle tables from looking like someone had spilled alphabet soup into a laboratory notebook. The Eightfold Way arranged hadrons into families according to shared properties. Particles could be placed on diagrams using features such as electric charge and strangeness. When arranged this way, baryons and mesons fell into striking patterns. Some groups contained 8 particles, others contained 10. The shapes of these groupings were not arbitrary. They reflected a deeper mathematical symmetry that physicists called flavor symmetry. Flavor, in particle physics, does not mean taste. There is no vanilla quark, which is probably for the best. Flavor is the name given to different types of particles that share certain broad behaviors, but differ in properties such as mass and charge. At this stage, the relevant flavors were connected with what would soon be understood as up, down, and strange quarks. The remarkable thing about the Eightfold Way was that it did more than organize what was already known. It predicted something new. One of the most famous patterns involved a group of baryons known as the baryon decuplet. This arrangement had a missing place. If the symmetry was real, there ought to be another particle with very specific properties. Gell-Mann predicted the existence of this particle, including its electric charge, strangeness, and approximate mass. It became known as the omega-minus baryon. In 1964, the omega-minus baryon was observed at Brookhaven National Laboratory. Its discovery was a triumph for the Eightfold Way. A particle that had been expected from symmetry had appeared in experiment, with the properties the pattern required. That mattered enormously. A classification scheme can always tidy up a mess after the fact. Given enough patience, you can arrange almost anything into categories. Books on a shelf, socks in a drawer, biscuits by how emotionally necessary they feel at 11:30 at night. But prediction is different. Prediction means the pattern is not merely decorative. It means the pattern may be pointing toward a real structure beneath the surface. This is one of the quiet powers of symmetry in physics. A symmetry is a feature of a system that remains unchanged under some transformation. A snowflake may look similar after being rotated by certain angles. The laws of physics appear to work the same in different places in space. Conservation laws, such as conservation of energy and conservation of momentum, are deeply connected to symmetries through the work of Emmy Noether. In particle physics, symmetry can reveal relationships between particles even before the deeper reason for those relationships is fully understood. The Eightfold Way worked in this spirit. It did not begin by directly opening up a proton and finding smaller pieces sitting inside. Instead, it noticed that hadrons behaved as if they belonged to organized families. The symmetry was like a shadow cast by something hidden. Physicists could see the shadow clearly before they knew exactly what object was casting it. This is where quarks began to enter the story. At first, quarks were not introduced because someone had seen a single quark drifting through a detector. No one had. They were introduced because the patterns among visible particles needed an explanation. The hadrons of the particle zoo seemed to be built from smaller underlying ingredients. If those ingredients existed, then the families of particles could be understood as different combinations of them. That was a strange kind of discovery. Usually we imagine particles being found directly, like tiny specks appearing in the data. But quarks first appeared as an answer to a pattern. They were suggested by order, not by isolation. Their existence was inferred from the way hadrons grouped together, the way missing particles could be predicted, and the way the whole particle zoo seemed to whisper that it was not the deepest layer. This connects directly to the central mystery. The particle that can never exist alone did not first arrive as a lonely particle at all. It arrived as a hidden explanation for particles that could be observed. Quarks were introduced to make sense of hadrons, yet from the beginning they carried an unusual tension. They seemed necessary, they seemed powerful, they made the patterns clearer. But if they were real particles, where were they? The answer would become one of the defining ideas of modern particle physics. Quarks could be real, fundamental and essential, while still remaining permanently confined inside the matter they helped create. The patterns had pointed towards something hidden. Now physicists needed to decide what that hidden thing might be. In 1964, Murray Gell-Mann and George Zweig independently proposed a new idea. The crowded families of hadrons could be understood if they were not fundamental particles at all. Instead, hadrons might be built from smaller constituents. Gell-Mann called these constituents quarks. Zweig called them aces. Both ideas were pointing in the same direction, but Gell-Mann's name became the one that stayed. It was borrowed from a line in James Joyce's novel Finnegan's Wake, which is a pleasingly odd origin for one of the most important words in modern physics. The universe, apparently, does not mind a little literary flourish at the bottom of matter. The first version of the quark model used three kinds of quark. These were the up quark, the down quark, and the strange quark. In particle physics, these different kinds are called flavors. This does not mean anything is being tasted. No physicist is gently sampling a proton and deciding it has notes of down quark with a strange finish. Flavor is simply the name for the type of quark. The up quark, down quark, and strange quark have different masses, different electric charges, and different roles in building hadrons. The electric charges were especially surprising. The proton has one full positive unit of electric charge. The electron has one full negative unit of electric charge. In ordinary chemistry and electricity, charge usually appears in whole number units when compared with the proton's charge, but quarks seem to carry fractional charges. The up quark has positive 2/3 of the proton's charge. The down quark has negative 1/3 of the proton's charge. The strange quark also has negative 1/3 of the proton's charge. This was not a small detail. It was deeply strange. No one had ever observed a free particle with 1/3 or 2/3 of the proton's charge. Every freely observed particle seemed to carry charges that added up in whole units. And yet, if quarks carried fractional charges, the hadron patterns suddenly made sense. A proton, for example, contains 2 up quarks and 1 down quark. 2 up quarks contribute positive 2/3 plus positive 2/3. 1 down quark contributes negative 1/3. Put together, this gives one full positive charge, so the proton's charge comes out exactly right. A neutron contains 1 up quark and 2 down quarks. The up quark contributes positive 2/3. The 2 down quarks contribute negative 1/3 and negative 1/3. The total is 0. So the neutron has no overall electric charge. This was elegant. It was almost suspiciously elegant, which in physics is often when people start paying close attention. The quark model also explained broader families of hadrons. Baryons, such as protons and neutrons, could be understood as particles made from 3 quarks. Other baryons contained strange quarks as well, which helped explain the strange particles discovered in cosmic rays and accelerator experiments. Mesons, meanwhile, could be understood as combinations of 1 quark and 1 antiquark. An antiquark is the antimatter partner of a quark. It has related properties but opposite charge and opposite versions of certain quantum numbers. Pions and kaons, 2 important kinds of meson, fit naturally into this scheme. What had looked like a growing zoo of unrelated particles began to look more like combinations made from a smaller set of ingredients. The model did something powerful. It simplified without erasing complexity. Instead of treating every hadron as a completely separate object, physicists could describe them as different arrangements of quarks and antiquarks. The particle zoo began to look less like a random crowd and more like a language, with hadrons as words and quarks as letters. But there was a serious problem. If quarks were real particles, why could no one find one alone? That question made some physicists cautious. Perhaps quarks were not physically real in the usual sense. Perhaps they were only a useful mathematical device, a way of organizing patterns without existing as individual objects. Their fractional charges made the worry stronger. If a quark with positive 2/3 of a proton's charge really existed, why had no experiment seen such a charge moving by itself? This hesitation was reasonable. Science does not accept hidden ingredients just because they make a diagram look tidy. A model must connect with measurable reality. Quarks explained hadron patterns beautifully, but they seem to refuse the most direct kind of evidence: isolated detection. So the quark model arrived with a strange double character. On one side, it made the known particles fall into place with remarkable clarity. It explained the proton, the neutron, mesons, baryons, strangeness, and the success of the eightfold way. On the other side, it introduced particles that appeared to be impossible to extract. The quark was becoming indispensable, but not available, and that is what makes it so central to this story. It was not just a smaller piece of matter waiting patiently inside the proton. It was a new kind of ingredient, one that could explain the visible world while remaining hidden from solitary view. The particle that can never exist alone had finally been named. The quark model was elegant, but elegance alone is not enough. Physics is full of beautiful ideas, and not all of them survive contact with experiment. A theory may arrange particles neatly, explain old patterns, and make the blackboard look deeply satisfying, but at some point nature has to answer back. In the case of quarks, the answer came from firing very energetic electrons into protons and watching how they scattered. The experiments took place in the late 1960s at the Stanford Linear Accelerator Center, often called SLAC. This facility used a long linear accelerator to produce high-energy electrons. These electrons were then aimed at targets containing protons. The goal was to probe the inside of the proton with far greater sharpness than earlier experiments had been able to achieve. The method was called deep inelastic scattering. That phrase sounds rather severe, but the basic idea is calm enough. An electron is a small charged particle. Because it is much lighter than a proton and does not experience the strong interaction in the same way, it can be used rather like a tiny probe. When an energetic electron approaches a proton, it interacts mainly through the electromagnetic force. By studying how the electron changes direction and energy after the collision, physicists can infer what kind of structure it encountered inside the proton. It is a little like trying to learn the shape of something hidden in a dark room by bouncing small objects off it and listening carefully. Though in this case the objects are electrons, the room is a proton, and the listening equipment is a major national laboratory, so it is not quite the same as misplacing your slippers. Jerome Friedman, Henry Kendall, and Richard Taylor played central roles in these experiments, along with their collaborators. Their work revealed that protons were not smooth, featureless blobs of charge. Instead, the scattering patterns suggested that the charge and momentum inside the proton were concentrated in smaller point-like constituents. Friedman, Kendall, and Taylor later received the Nobel Prize in Physics for this work. The logic had a beautiful historical echo. More than half a century earlier, Ernest Rutherford had fired alpha particles at thin gold foil and discovered the atomic nucleus. Most alpha particles passed through, but a few scattered sharply, revealing that positive charge and mass were concentrated in a tiny central region. Rutherford used deflection to reveal hidden structure inside the atom. The deep, inelastic scattering experiments did something similar, but one layer deeper. Instead of probing atoms to find nuclei, they probed protons to find smaller internal constituents. The energies were vastly higher, the distances were far smaller, and the equipment was far more sophisticated, but the principle was familiar. When particles scatter, their paths can reveal what they struck. The word inelastic is important. In elastic scattering, the target remains essentially unchanged, like a gentle bounce. In deep inelastic scattering, the proton is struck so hard that it can break apart into a spray of other particles. The collision is violent enough to reveal internal structure, not merely nudge the proton as a whole. What the experiments found was startling. At very short distances, the constituents inside the proton behaved almost as if they were independent. They seemed point-like, compact, and able to carry definite portions of the proton's momentum. This was exactly the sort of thing the quark model needed, but the story was still not quite finished. Richard Feynman introduced a helpful way of thinking about the results. He described the proton as containing point-like objects called partons. In a very high-energy collision, the electrons seemed to scatter from these partons almost as though they were free particles inside the proton. The parton model gave physicists a practical language for understanding the data before the full theory of quarks and gluons was firmly established. Later, partons were identified with quarks and gluons. Quarks carry electric charge and help form the identity of particles such as protons and neutrons. Gluons carry the strong interaction between quarks. Together they create the rich internal life of the proton. But the deep inelastic scattering results created a fascinating tension. On one hand, they strongly supported the reality of quark-like constituents. The proton was not a simple little sphere. It had an interior. It contained smaller objects that behaved like point-like particles when struck at high energy. This was powerful evidence that the quark model was not just a clever classification scheme. On the other hand, no individual quark came flying out of the proton and travelled alone into the detector. This is the strange contrast at the heart of the subject. Inside the proton, under violent short-distance probing, quarks can behave almost as if they are free. But when the collision is over, nature does not present a single isolated quark. Instead, the energy of the strong interaction produces new colour-neutral particles. The detector sees hadrons, not lonely quarks. The evidence was therefore both revealing and mysterious. It showed that protons contain point-like constituents, yet it also preserved the rule that those constituents cannot be separated in the ordinary way. The quark became more real than ever, but also more deeply confined. It was as if nature had opened the proton just wide enough for physicists to glimpse the hidden pieces inside, then quietly closed the door before any one of them could leave alone. There was still one more hidden property needed to make the quark model work. It had a wonderfully misleading name. Physicists called it colour. Colour charge has nothing to do with visible colour. A quark is not actually red, green, or blue in the ordinary sense. If you could somehow look at one, which confinement strongly objects to, you would not see a tiny glowing bead painted like a traffic light. The words red, green, and blue are labels for a mathematical property involved in the strong interaction. They are useful names, not literal colours. But this new kind of charge turned out to be essential. In electromagnetism, particles can have electric charge. Electrons have negative electric charge. Protons have positive electric charge. Photons interact with electrically charged particles, but photons themselves do not carry electric charge. The strong interaction works differently. Quarks carry colour charge, and the force connected with colour charge is the strong interaction, later described by the theory called quantum chromodynamics. The idea of colour charge developed through the work of several physicists including Oscar Greenberg, Yoichiro Nambu, Mu-Young Han, and Harold Fritsch. These ideas helped prepare the ground for quantum chromodynamics, the modern theory of quarks, gluons, and the strong force. At first, colour charge was introduced partly because the quark model had a serious problem. One important example was the omega- baryon. This particle had been predicted by the Eightfold Way, and then discovered at Brookhaven National Laboratory in 1964. It fit the pattern beautifully. But in the quark model, the omega- baryon appeared to contain three strange quarks, arranged in what seemed to be the same quantum state. That caused trouble with the Pauli exclusion principle. The Pauli exclusion principle, introduced by Wolfgang Pauli in 1925, says that certain particles called fermions cannot occupy exactly the same quantum state at the same time. Quarks are fermions, so if three strange quarks inside the omega- baryon seemed identical in every relevant way, the arrangement should have been forbidden. The solution was colour charge. If each strange quark had a different color charge, then they were not truly identical in every quantum property. One could be labeled red, one green, and one blue. Again, these are not real colors, but names for three distinct types of color charge. With this extra property included, the omega- baryon no longer violated the Pauli exclusion principle. The quarks could occupy the same kind of spatial arrangement while differing in color charge. It was an elegant rescue. And as often happens in physics, the rescue became much more than a convenient patch. Color charge changed the entire understanding of the strong interaction. It suggested that quarks are not merely small pieces sitting inside hadrons, but particles governed by a deeper rule. Observable particles must be color neutral overall. In ordinary language, they must combine their color charges so that no net color charge is left exposed. A baryon, such as a proton or neutron, contains three quarks. In the color picture, those three quarks combine one red, one green, and one blue color charge into a color-neutral whole. It is a little like mixing the labels together so that the final object carries no exposed color charge. The comparison is not exact because this is quantum mathematics rather than paint, but it gives the right feeling. The individual charges balance into something neutral. A meson works differently. It contains one quark and one antiquark. The quark carries color charge, while the antiquark carries the corresponding anticolor charge. Color and anticolor combine into a color-neutral particle. So mesons, like baryons, can exist as observable particles because they hide their color charge inside an overall neutral structure. This is where the title becomes sharper. Quarks are not merely difficult to isolate because experiments are not powerful enough. The deeper issue is that a single quark carries color charge, and freely observable particles are color neutral. A lone quark would be an exposed color-charged object, but nature does not seem to allow such objects to appear alone in the ordinary world. That is the heart of confinement. Every time quarks appear in the particles we can observe, they appear in combinations. Three quarks can make a baryon. A quark and an antiquark can make a meson. More exotic arrangements are possible too, as long as the final particle is color neutral, but the single quark remains hidden because it cannot cancel its color charge by itself. This does not mean color charge is unreal. Quite the opposite. It is one of the defining properties that makes quarks behave the way they do. It explains why the strong interaction has its particular structure, why hadrons form as they do, and why the quark model could satisfy the Pauli exclusion principle in particles like the omega- baryon. The name may be playful, but the principle is serious. At the deepest levels of ordinary matter, nature keeps a kind of accounting system. Electric charge must balance in certain ways. Energy and momentum must be conserved. Quantum states must obey the Pauli exclusion principle, and color charge must be hidden inside color-neutral combinations. So the quark is trapped not by a tiny wall, not by a miniature cage, and not by stubbornness, though it does give that impression. It is trapped by the rules of the strong interaction itself. The particle that can never exist alone is bound by a charge that can never be left exposed. If quarks carry color charge, then something has to carry the force between them. That something is the gluon. A gluon is the force-carrying particle of the strong interaction. In a very loose comparison, gluons play a role in the strong force a little like the role photons play in electromagnetism. Photons are the particles associated with light and electromagnetic radiation. They are also the force carriers of the electromagnetic interaction between electrically charged particles. When electrons repel other electrons or when electrons are attracted to protons, the interaction can be described through the exchange of photons. That comparison is useful, but only up to a point, because gluons are much stranger. Photons do not carry electric charge. A photon can carry energy and momentum, but it does not itself have positive or negative electric charge. This means photons do not directly attract or repel other photons in ordinary electromagnetic theory. Light beams can pass through one another without behaving like two streams of charged matter colliding in the middle of the room, which is helpful, really. Otherwise, opening the curtains would be a much more dramatic event. Gluons are different because gluons carry colour charge. This is the key difference. Quarks carry colour charge, and gluons carry colour charge too. Because gluons carry the very kind of charge involved in the strong interaction, they can interact with other gluons. They are not just quiet messengers moving between quarks, they are part of the conversation themselves. This idea sits at the heart of quantum chromodynamics, the theory of quarks, gluons, and colour charge. Harold Fritsch, Murray Gell-Mann, Heinrich Leutwiler, and other physicists helped develop the early framework of quantum chromodynamics in the early 1970s. The name means, roughly, the quantum theory of colour dynamics. It is the part of the standard model that describes the strong interaction. Quantum chromodynamics is a quantum field theory. That means it does not treat particles as tiny hard balls moving through empty space in a simple classical way. Instead, it describes fields spread throughout space-time, with particles appearing as excitations of those fields. Quarks are excitations of quark fields. Gluons are excitations of the gluon field. The strong interaction is the behaviour of these fields and their exchanges of energy, momentum and colour charge. Inside a proton or neutron, quarks interact by exchanging gluons. These gluons change the colour charge of quarks as they move between them. A quark may begin with one colour charge and end with another, while the gluon carries away the difference. This colour exchange is not a decorative detail, it is the machinery of the strong force. But because gluons also carry colour charge, the gluon field is highly active. Gluons can emit gluons. Gluons can absorb gluons. Gluons can interact with one another in a way photons do not normally do. The result is that the strong force has a rich, tangled inner life. This self-interaction is one reason the strong interaction behaves so differently from electromagnetism. With electromagnetism, the force between two electric charges spreads outward through space and weakens with distance. If two charged particles are moved farther apart, the electric force between them becomes smaller. This is familiar from classical physics and from Coulomb's law. Distance softens the interaction. Between quarks, the story is not so simple. At the scale of hadrons, such as protons and neutrons, the strong field does not simply spread out thinly in all directions in the ordinary electromagnetic way. The gluon field tends to concentrate the strong interaction between colour-charged particles. A useful image is a tightening tube or strand of field energy stretching between quarks. The comparison is not perfect, but it captures the important feeling. Pulling quarks apart does not make the force gently fade into nothing. Instead, energy builds in the strong field. This is part of the road toward confinement. If you try to separate two quarks, the gluon field between them stores more and more energy. Eventually, instead of allowing a single quark to escape, that energy can produce new quark and antiquark pairs. The result is not one lonely quark and one lonely partner drifting away. The result is new colour neutral hadrons. So gluons are not just the glue in a simple mechanical sense. The name is memorable and reasonably accurate, but it can make the picture sound too ordinary. They are not little blobs of adhesive between tiny beads. They are quantum excitations of a self-interacting field, carrying colour charge, constantly shaping the inside of hadrons. This also helps explain why a proton is not simply three quarks sitting still. A proton contains three valence quarks, but it also contains a dynamic sea of gluons, quark and antiquark pairs, and field energy. Much of the proton's mass comes not from the small bare masses of the quarks themselves, but from the energy of the strong interaction inside it. The proton is less like a little bag holding three marbles, and more like a stable storm of quantum chromodynamics. A very well-behaved storm, thankfully. One that has agreed to form atoms, chemistry, planets, and cups of tea. The gluon therefore deepens the mystery of the quark. Quarks cannot be understood without gluons, and gluons cannot be understood as passive carriers. The messenger also feels the force. The field that binds quarks together also binds itself into the behavior of matter, and because gluons carry color charge, the strong interaction becomes powerful in a way no ordinary everyday force quite prepares us for. The particle that can never exist alone is held there by messengers that are also trapped in the same hidden web. The strong force has a rather unusual personality. At first, it sounds as if it should be simple. If it is called the strong force, then surely it is just strong. Strong up close, strong far away, strong in the morning, strong after a cup of tea. But quantum chromodynamics does not behave quite so politely. The strength of the interaction depends on the scale at which it is being tested. This is where one of the strangest discoveries in modern particle physics enters the story. It is called asymptotic freedom. Asymptotic freedom means that quarks interact more weakly when they are extremely close together or when they are probed at very high energies. At shorter and shorter distances, the strong interaction between quarks becomes less intense. The quarks begin to behave almost as if they are free particles, even though they're still inside a proton, neutron, or another hadron. That sounds backwards. After all, the strong force is supposed to be the force that confines quarks. It is the force that stops them from appearing alone. So how can quarks seem freer when examined more closely? The answer was developed in 1973 by David Gross, Frank Wilczek, and David Politzer. Their work showed that quantum chromodynamics has a special property. The effective strength of the strong interaction changes with energy scale. They later received the Nobel Prize in Physics for this discovery. The word effective is important. It does not mean the theory is pretending. It means that the measured strength of an interaction can depend on the conditions under which it is observed. In quantum field theory, empty space is not simply empty in the ordinary sense. Quantum fields can fluctuate. Particles and antiparticles can briefly affect how forces appear at different distances. The result is that the strength of an interaction can run, meaning it changes with scale. In electromagnetism, this running exists too, but it behaves differently. At shorter distances, the electric charge of a particle can appear slightly stronger, because quantum effects screen and reveal charge in a particular way. In quantum chromodynamics, the self-interacting gluon field produces the opposite kind of behavior. At very short distances, the strong coupling becomes weaker. This explains something that had puzzled physicists after the deep, inelastic scattering experiments at the Stanford Linear Accelerator Center. Those experiments fired high-energy electrons into protons. The electrons scattered as though they had struck point-like objects inside the proton. Richard Feynman called these objects partons. During the brief, violent collision, the partons seemed almost independent. They did not behave like constituents held tightly in place by an overwhelmingly strong force. They behaved more like small objects moving within the proton, capable of being struck individually. Asymptotic freedom made sense of this. At the tiny distance scales reached in high-energy collisions, quarks interact more weakly with one another. So, for the brief instant of the collision, a quark can behave almost like a free particle. This is why the parton model worked so well. The electron was not seeing a smooth proton. It was seeing compact internal constituents whose behavior matched what the quark model suggested. But this freedom is not ordinary freedom. A quark that behaves almost freely inside a proton during a high-energy interaction is not the same as a quark escaping from the proton and travelling alone through a detector. It is a little like seeing someone move freely inside a room, then assuming they must also be able to leave the building. In this case, the building is guarded by quantum chromodynamics, which is not known for letting people wander off without paperwork. When the collision is over, confinement still takes over. The struck quark does not emerge as a solitary object. Instead, the energy involved in the collision produces jets of hadrons. The quark turns into a stream of color-neutral particles through the process of hadronization. Detectors see the aftermath, not an isolated quark. This is the delicate balance at the heart of quantum chromodynamics. At very short distances, quarks are nearly free. At larger distances, the force becomes stronger. The same theory explains both behaviours. It explains why deep inelastic scattering revealed point-like constituents inside protons, and why those constituents never appear alone afterward. The phrase asymptotic freedom describes what happens as the distance becomes extremely small, or the energy becomes extremely high. The quarks approach a state of freedom, but only in that limiting short-distance sense. The word asymptotic is doing quite a lot of quiet work here. It means the freedom is approached in a particular limit, not that the quark receives a tiny passport and strolls away into space. This gives the bridge to confinement. If quarks interact more weakly when they are very close together, then the reverse is also true in the relevant range. As quarks are pulled farther apart, the strong interaction does not fade gently like electromagnetism. It grows more important. The gluon field between them stores energy. The colour field tightens. Trying to separate quarks does not reveal them as lone particles. It creates the conditions for new hadrons to form. So the strong force is strange in both directions. Up close, it becomes quieter. Farther out, it becomes harder to escape. It allows quarks to move almost freely within the tiny interior of a proton, yet prevents them from existing alone in the wider world. The quark is therefore not simply locked in place like a stone in a wall. It is part of a dynamic quantum system, freer than expected at the smallest distances, and more confined than anything familiar when separation is attempted. The deeper physicists looked, the more the quark seemed to whisper, "Close enough, and I almost behave like I am free. Pull me away, and the universe will build something else before I can ever be alone." This is the point where the mystery becomes its clearest. Quark confinement is the observed and theoretically expected fact that particles carrying colour charge are not found alone. Individual quarks carry colour charge. Gluons carry colour charge as well. But the particles that travel freely through detectors form ordinary matter and appear as independent objects are colour neutral overall. A lone quark would have exposed colour charge, and nature seems to forbid that situation. This is not just a small technical detail. It is one of the defining features of the strong interaction. In everyday thinking, pulling two things apart usually makes their connection weaker. If two magnets are moved farther away from each other, the force between them drops. If two electrically charged particles are separated, the electromagnetic force between them becomes weaker with distance. This feels natural to us because it is how many familiar forces behave. But quarks do not follow that comfortable pattern. When quarks are extremely close together, asymptotic freedom allows them to behave almost like free particles inside a hadron. But when you try to pull them apart, the strong interaction does not simply fade away. Instead, the field between them stores more energy. The farther the separation grows, the more serious the problem becomes. A useful picture is the colour flux tube. In this image, the strong field between quarks does not spread out thinly through space in all directions like the electric field around a charge. Instead, it becomes concentrated into a narrow tube of field energy stretching between colour charges. The quarks are connected by a kind of invisible strand of strong interaction energy. This is only a picture, not a literal glowing string inside the proton, but it helps capture the unusual behaviour. The comparison often used is an elastic band. If you pull an elastic band, energy is stored in it. Pull harder, and the band stretches more. With quarks, something vaguely similar happens in the colour field between them. Trying to separate quarks stores energy in the strong field, but the comparison has to be handled carefully because the quantum world adds a very important twist. An ordinary elastic band might eventually snap. The strong field does something stranger. When enough energy is stored in the colour flux tube, that energy can be converted into matter. More specifically, it can create a new quark and antiquark pair. This is possible because in modern physics, energy can become particles when the conditions allow it. The energy in the field does not free the original quark. It creates new partners. This process is often called string breaking. Imagine trying to pull a quark away from another quark. As the distance increases, the colour field between them grows more energetic. Eventually, instead of one quark escaping, the field produces a new quark and antiquark. The newly created particles pair up with the original ones, forming new colour neutral hadrons. So the attempted separation does not end with one isolated quark. It ends with more bound particles. This is the central answer to the title. The quark can never exist alone because the attempt to isolate it produces the conditions for new particles to appear. Nature does not hand you a single quark. It hands you hadrons. You pull at the hidden thread, and the universe quietly weaves more fabric, which is impressive, if slightly uncooperative. This is why particle detectors see jets rather than individual quarks. In a high-energy collision, a quark may be struck violently and may move away from the collision region. But as it moves, the strong field responds. New quark and antiquark pairs form. A spray of colour-neutral hadrons emerges. The original quark's presence is revealed by the pattern of the jet, not by a lonely track marked quark. Confinement is deeply supported by experiment. No free quark has ever been observed, despite many searches. Fractional electric charges like positive 2/3 or negative 1/3 of the proton's charge appear inside the theory and inside hadron structure, but not as charges carried by isolated particles drifting through ordinary space. It is also supported by computation. Kenneth Wilson made essential contributions to lattice gauge theory, a way of studying quantum field theories such as quantum chromodynamics, by placing them on a discrete grid of space-time points. Lattice quantum chromodynamics allows physicists to use powerful computers to explore the strong interaction in regimes where ordinary approximation methods fail. These calculations strongly support the picture of confinement and help reproduce the masses and behaviours of hadrons from the underlying theory of quarks and gluons. And yet, there is still a deep mathematical subtlety. Confinement is not a wild guess. It is one of the most reliable and experimentally grounded facts about the strong interaction. But a complete, rigorous proof of confinement in quantum chromodynamics remains one of the major unsolved problems in theoretical physics. The evidence is strong, the calculations are powerful, the physical picture is compelling. But the final mathematical foundation is still not fully complete. That makes confinement especially beautiful. It is not merely a prison for quarks, it is a rule woven into the structure of matter itself. It explains why the proton stays whole, why quarks leave only indirect traces, and why the deepest pieces of ordinary matter cannot be separated like little beads from a necklace. The quark is real, it is fundamental, it helps build the visible world. But when you try to make it stand alone, the strong force answers by creating something else for it to belong to. If quarks cannot leave the detector as single particles, then how can physicists be so confident they are there? The answer is that quarks leave patterns. In high-energy particle collisions, physicists do not usually see the original quark itself. They see the aftermath. They see sprays of particles moving in particular directions, carrying particular energies, and forming shapes that match what quantum chromodynamics predicts. These sprays are called jets. A jet is not a single particle. It is a narrow stream of many particles produced after an energetic quark or gluon is created in a collision. The quark or gluon begins to move away from the collision point, but confinement prevents it from travelling alone. As it moves, the strong field responds. Energy turns into new quark and antiquark pairs. These combine into colour-neutral hadrons, such as pions, kaons, protons, and other particles. The detector records this stream, and from the stream physicists infer the original quark or gluon. This process is called hadronization. Hadronization is the transformation of energetic quarks and gluons into ordinary hadrons. It is one of the clearest practical demonstrations of confinement. The quark is created or struck at high energy, but it does not arrive at the detector as a bare colour-charged particle. It becomes part of a family of color-neutral particles moving in roughly the same direction. The quark does not escape, but it leaves a trail. A gentle comparison is footprints in soft ground. If someone walks across a muddy field at night, you may not see the person directly, but in the morning, the footprints are structured enough to tell you someone passed through. You can see the direction. You can estimate the stride. You may even infer something about the movement. The quark itself does not stroll into view, but the jet it leaves behind carries information about what happened. Some of the most important evidence for this came from electron and positron collisions. An electron is a negatively charged particle. A positron is its antimatter partner with positive charge. When an electron and a positron collide at high energy, they can annihilate and produce other particles. In certain collisions, the energy produces a quark and an antiquark moving in opposite directions. But because neither can exist freely, each one undergoes hadronization. The result is often two jets of particles, pointing roughly back to back. These two jet events provided strong evidence for quark and antiquark production. The detector did not see one quark on one side and one antiquark on the other. Instead, it saw two organized sprays of hadrons. The pattern made sense if a quark and antiquark had been produced and then transformed into color-neutral particles. But an even more important clue came from three jet events. Quantum chromodynamics predicts that an energetic quark can radiate a gluon, rather like an electrically charged particle can radiate a photon, though the details are very different. If a quark and antiquark are produced, and one of them emits a high-energy gluon, then the final event can produce three separate jets, one from the quark, one from the antiquark, and one from the gluon. This was a crucial test, because gluons had been introduced as the carriers of the strong interaction. They were central to the theory, but physicists needed experimental evidence that they behaved as real particles within high-energy events. A major milestone came in 1979 at the German electron synchrotron, often known by its German acronym DESI. The TASO collaboration observed three jet events in electron and positron collisions at the Petra storage ring. These events provided strong evidence for gluon radiation and became one of the landmark confirmations of quantum chromodynamics. The three-jet pattern was not random debris, it had structure. It matched the idea that the strong interaction involves quarks and gluons, and that gluons themselves can carry energy and momentum away from the collision. The gluon did not appear as a lonely particle any more than the quark did. It also had to become a stream of hadrons. But the shape of the event revealed its presence. Other accelerator facilities also studied jets in great detail. Experiments at the European Organization for Nuclear Research, Fermilab, the Stanford Linear Accelerator Center, and later the Large Hadron Collider refined the picture further. Jets became one of the central tools of particle physics, used to identify quarks, gluons, and the processes that create them. Jets connect directly back to confinement. If quarks were ordinary separable particles, a detector might see isolated fractional electric charges. It might see a quark track with positive 2/3 or negative 1/3 of the proton's charge. But that is not what happens. Detectors see color-neutral particles grouped into jets. The quark's energy, direction, and identity are translated into a hadronic spray. So confinement does not make quarks invisible in a simple sense. It makes them indirect. It hides them as solitary objects, while allowing their behavior to be reconstructed through the particles they produce. The quark never escapes alone, but it does leave fingerprints. And those fingerprints are written across the detectors in narrow streams of matter, showing that something color-charged was briefly there, before the strong force calmly gathered the evidence into hadrons. The quark model began with 3 flavors, but nature did not stop there. Today, physicists know of 6 quark flavors. They are the up quark, the down quark, the strange quark, the charm quark, the bottom quark, and the top quark. These 6 flavors belong to the standard model of particle physics, and they form one of the main families of elementary particles. The word flavor, again, is only a label for type. It does not mean the quarks have taste, scent, texture, or any other quality that would make a proton suitable for a menu. It simply means that quarks come in different kinds, each with its own mass, electric charge, and behavior under the fundamental forces. The up and down quarks are the lightest and most familiar, although familiar is a generous word for something no one has ever seen alone. They make up the ordinary protons and neutrons inside atomic nuclei. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Almost all ordinary matter around us depends on these 2 flavors. The strange quark was added to explain strange particles, such as kaons and certain heavier baryons. These particles appeared in cosmic ray and accelerator experiments and behaved in ways that hinted at a new conserved property called strangeness. The strange quark helped turn that pattern into a clearer physical picture. But the next flavor, charm, arrived through a mixture of theory and dramatic discovery. In the 1960s and early 1970s, physicists including Sheldon Glashow, James Bjorken, Sheldon Lee Glashow, John Iliopoulos, and Luciano Maiani helped develop ideas pointing toward the charm quark. One major reason for expecting charm came from the need to explain certain weak interaction processes and make the emerging particle theory behave properly. The Glashow-Iliopoulos-Maiani mechanism, proposed in 1970, helped show why a 4th quark could solve serious problems in the theory of weak interactions. Then, in 1974, something remarkable happened. Experiments at Brookhaven National Laboratory and the Stanford Linear Accelerator Center independently discovered a new particle known as the J-psi particle. It was unusually long, lived for its mass, and appeared as a sharp, clear signal in the data. The discovery caused such excitement that it became known as the November Revolution in particle physics. The J-psi particle was understood as a bound state of a charm quark and a charm antiquark. Its discovery strongly supported the existence of the charm quark and helped convince physicists that the quark model was not just a useful organizing trick, it was describing real constituents of matter. Then came the bottom quark. In 1977, the bottom quark was discovered at Fermilab through the observation of particles called upsilon mesons. These were interpreted as bound states involving a bottom quark and a bottom antiquark. The discovery added a 5th quark flavor and strengthened the idea that quarks came in generations, paired with the structure of leptons in the standard model. The top quark was the last and heaviest quark to be found. It was discovered in 1995 at Fermilab by the Collider detector at Fermilab and D0 collaborations. The top quark is extraordinarily massive compared with the other quarks. It is heavier than an entire tungsten atom, even though it is an elementary particle as far as current experiments can tell. This is one of those facts that sounds as if physics has slightly lost control of the filing system, but it is real. The top quark is also unusual because it decays extremely quickly. It is so short-lived that it decays before it has time to form ordinary hadrons in the usual way. Most quarks, when produced, are quickly wrapped into color-neutral particles through hadronization. The top quark disappears through decay before that process can properly happen. But this does not mean the top quark is observed as a stable isolated quark. It is detected through its decay products. Physicists reconstruct its presence from the particles it produces, the energies involved and the patterns predicted by the standard model. Even here, at the edge of what quarks can do, the rule remains subtle but firm. A top quark does not calmly drift through a detector as a long-lived, freely isolated object with exposed color charge. So the 6 flavors form a kind of hidden family. Up and down quarks build the stable matter of everyday life. Strange quarks appear in heavier unstable hadrons. Charm and bottom quarks show up in particles produced in high-energy collisions. The top quark appears only fleetingly, decaying almost immediately after it's created. Their masses vary enormously, from the very light up and down quarks to the extremely heavy top quark. Yet all of them belong to the same deeper story. They carry colour charge, they participate in the strong interaction, they are described by quantum chromodynamics, and except for the special case of the top quark decaying before hadronization, they appear through bound systems rather than as solitary particles. From the light quarks inside the atoms of your hand to the heavy quarks briefly created in the most powerful machines on Earth, confinement remains one of the great rules. Quarks may come in 6 flavours, but none of those flavours includes freedom. A proton sounds at first like it should be fairly simple. It has positive electric charge. It sits inside atomic nuclei. It helps define which element an atom belongs to. Hydrogen has 1 proton, carbon has 6 protons, oxygen has 8 protons. If you change the number of protons, you change the element itself, so it is natural to imagine the proton as a small, solid, well-defined object, perhaps made from 3 quarks sitting neatly inside it. But the proton is not neat. The simplest description says that a proton contains 2 up quarks and 1 down quark. That is true, but it is not the full story. Those 3 quarks are called valence quarks. They determine the proton's basic identity, including its electric charge and many of its quantum properties. 2 up quarks and 1 down quark give the proton 1 full positive charge. In that sense, the valence quarks are essential. Yet if we look at the proton's mass, something surprising happens. The up and down quarks inside a proton are very light. Their individual masses are only a few million electron volts in energy units. A proton, by contrast, has a mass of about 938 million electron volts. Even if you add the masses of the 2 up quarks and the 1 down quark, you get only a small fraction of the proton's total mass. Most of the proton's mass does not come directly from the bare masses of the quarks. It comes from energy. This is one of the deep lessons of modern physics. Einstein's mass-energy relation tells us that mass and energy are not completely separate things. In spoken form, the idea is mass and energy are equivalent, and energy divided by the speed of light squared contributes to mass. The exact equation is famous, but the meaning is the important part here. Energy can show up as mass. A system can weigh more because of the energy stored inside it. Inside a proton, there is a great deal of energy. The quarks are not sitting still. They are quantum objects moving and interacting within a tiny region. Gluons are constantly exchanged between them. The gluon fields themselves carry energy. The strong interaction creates a restless internal structure, full of field energy, motion, and temporary quantum activity. The proton is less, like 3 marbles glued together, and more like a stable storm held in a very small space. A very small and extremely reliable storm, thankfully. If protons were more temperamental, chemistry would be a rather short-lived hobby. The proton also contains more than just 3 valence quarks in a simple everyday sense. Quantum chromodynamics describes a richer interior, including C-quarks and antiquarks. These C-quarks are not permanent identity markers in the same way as the valence quarks, but they arise from the fluctuating quantum fields inside the proton. Gluons can create quark and antiquark pairs, and those pairs can vanish again. The proton's interior is alive with these temporary contributions, so the valence quarks determine what the proton is, but the C-quarks, antiquarks, gluons, and field energy help determine how the proton behaves. This is why the phrase made of quarks is both true and slightly misleading. A proton is made of quarks in the sense that quarks are essential to its structure and identity, but it is also made of gluon fields, quantum motion, and strong interaction energy. It is not a tiny container with exactly 3 little balls inside. It is a color-neutral quantum system, constantly shaped by quantum chromodynamics. Modern experiments continue to study this internal structure in great detail. Jefferson Lab investigates how quarks and gluons contribute to the properties of protons and neutrons, using high-energy electron beams to probe nuclear matter. The European Organisation for Nuclear Research studies proton structure through high-energy collisions, including the proton beams of the Large Hadron Collider. These experiments help reveal how momentum, spin, and energy are distributed inside hadrons. Calculations from lattice quantum chromodynamics also play an important role. By placing quantum chromodynamics onto a discrete grid of spacetime points, physicists can use powerful computers to calculate properties of hadrons from the underlying theory. These calculations help explain why protons and neutrons have the masses they do. They support the picture that most of the visible mass of ordinary matter arises not from the bare masses of elementary quarks, but from the energy of the strong interaction. This is a remarkable thought. Most of the mass in the atoms around you comes from protons and neutrons. Most of the mass of protons and neutrons comes from the dynamics of quarks and gluons. So much of the weight of everyday matter, the heaviness of a book, the solidity of a stone, and the presence of your own body is rooted in the confined energy of the strong force. Confinement is therefore not only a rule about why quarks cannot exist alone, it is part of the reason matter has mass and stability at all. The same force that prevents a quark from wandering freely also helps create the protons and neutrons that make atoms possible. The hidden binding is not just a prison, it is a source of structure. It turns restless quantum fields into stable particles, and stable particles into the nuclei of the elements. So when we say a proton contains quarks, we are saying something true. But the deeper truth is richer and stranger. A proton is a bound state of valence quarks, C-quarks, antiquarks, gluons, motion, and energy, all held together by quantum chromodynamics. The particle that can never exist alone does not merely hide inside matter. It helps give matter its weight. There is another way to study quarks, and it does not begin by smashing particles together. It begins by turning space-time into a grid. This approach is called lattice quantum chromodynamics. It is one of the most important tools physicists use to study the strong interaction. Quantum chromodynamics describes quarks, gluons, color charge, and the forces that bind hadrons together. But the theory is extremely difficult to solve in the situations where confinement matters most. The mathematics becomes so intense that ordinary pen and paper methods often cannot carry the whole weight. So physicists found a different path. In lattice quantum chromodynamics, spacetime is represented as a discrete lattice, a kind of four-dimensional grid. Instead of treating space and time as perfectly continuous for the purpose of calculation, physicists place quantum chromodynamics onto this grid and calculate how quark and gluon fields behave at the grid points and between them. The lattice is not meant to say that space-time is definitely made of tiny squares. It is a calculation method, a way of making a fiercely difficult theory manageable. Kenneth Wilson was a central figure in developing lattice gauge theory. His work showed how theories like quantum chromodynamics could be studied non-perturbatively, meaning without relying on the usual kind of small correction method. This was crucial, because confinement is precisely where simple approximation methods struggle. In many parts of physics, a problem can be solved by starting with an easy version and then adding small corrections. If the correction is tiny, the method works beautifully. But in quantum chromodynamics, the strong coupling changes with scale. At very short distances, asymptotic freedom means quarks interact relatively weakly. There, approximation methods can work well. But at the larger distances where hadrons form, the strong coupling becomes large. The corrections are no longer small. The neat calculation begins to misbehave, rather like a tidy notebook left unattended near a cup of tea. This is the non-perturbative challenge. Confinement happens in the regime where the strong interaction is powerful. Quarks and gluons are not gently interacting particles that can be treated almost independently. They are part of a deeply connected quantum field system. The gluon field self-interacts. Quarks create and respond to changing color fields. C-quarks and antiquarks flicker through the description. The proton becomes a full quantum storm rather than a simple three-body problem. Lattice quantum chromodynamics allows physicists to explore this storm numerically. Using supercomputers, researchers can simulate the behavior of quark and gluon fields on the lattice. These calculations can estimate the masses of hadrons, study the forces between quarks, investigate the structure of protons and neutrons, and test whether quantum chromodynamics produces the particles seen in experiment. The calculations are enormously demanding because they involve huge numbers of variables and must carefully approach the limit where the artificial grid spacing becomes small enough to reflect the continuous theory. The results have been deeply important. Lattice calculations have successfully reproduced many properties of hadrons, including masses of particles made from quarks. This is one of the strongest reasons physicists trust quantum chromodynamics as the correct theory of the strong interaction. The theory does not merely name quarks and gluons. When placed on a lattice and calculated with enough care, it produces the world of hadrons that experiments observe. Research efforts at institutions such as Fermilab, Jefferson Lab, the European Organisation for Nuclear Research, and major university lattice groups have helped develop this field. Across the world, collaborations use advanced computing to study problems that cannot be reached by direct calculation alone. The work is slow, technical, and not usually as visually dramatic as a giant detector surrounding a collision point. But it is one of the quiet engines of modern particle physics. It gives physicists a way to ask whether the theory really builds protons, and the answer, again and again, is yes. This matters for confinement because confinement is not simply an experimental absence. It is not just that no one has happened to see a free quark. Lattice quantum chromodynamics shows that the underlying theory itself produces a world in which color-charged particles are bound into color-neutral hadrons. The same framework that describes quarks and gluons also supports the rule that they do not appear alone. Of course, numerical evidence is not the same as a complete formal proof. Lattice methods are powerful, but they rely on computation, approximations, and careful extrapolations. A rigorous mathematical proof of confinement in quantum chromodynamics remains an open challenge. Still, the agreement between lattice calculations, accelerator experiments, and the broader standard model is extraordinary. This makes confinement feel less like a mystery invented by missing evidence, and more like a deep feature repeatedly confirmed from different directions. Experiments reveal jets instead of solitary quarks. Hadron spectroscopy reveals families of bound states. Proton structure measurements reveal quarks and gluons moving inside hadrons. Lattice calculations show that quantum chromodynamics can generate the masses and behaviors of those hadrons from the underlying fields. So the strong force is not only seen in detectors, it is also rebuilt inside computers, one lattice calculation at a time. The particle that can never exist alone is held not just by an observed rule, but by a theory so rich that even our most powerful machines must patiently approximate its hidden geometry. Confinement is powerful, but it is not quite the same thing as saying quarks and gluons can never move through anything other than a proton or neutron. Under the right conditions, the familiar boundaries of hadrons can loosen. This brings us to one of the most extreme states of matter known in physics, quark-gluon plasma. It is a state in which quarks and gluons are no longer confined inside individual protons and neutrons in the ordinary way. Instead of being locked into separate hadrons, they move through a hot, dense medium where color charge is spread across a collective system. That distinction matters. Quark-gluon plasma does not mean physicists have bottled a single lonely quark and placed it gently on a laboratory shelf. No one has a little jar labelled free quark sitting beside the biscuits. What physicists create is a tiny, short-lived droplet of matter in which quarks and gluons are deconfined over a small region. They are not isolated as individual particles travelling through empty space. They are part of an extremely hot collective state. This state is thought to have existed naturally in the very early universe, Shortly after the Big Bang, the universe was far too hot and dense for ordinary protons and neutrons to exist as stable, separate particles. Matter was not yet arranged into atoms or nuclei, or even hadrons in the familiar sense. Quarks and gluons moved in an intensely energetic plasma. As the universe expanded and cooled, the conditions changed. The strong interaction brought quarks and gluons into colour, neutral hadrons. Protons and neutrons formed. Later still, nuclei and atoms could emerge. So the matter inside us may carry a memory, in a very broad physical sense, of a time when quarks and gluons were not yet locked into the familiar particles of the atomic nucleus. To study this ancient state, physicists create tiny versions of extreme early universe conditions in particle accelerators. The main method is heavy ion collision. Instead of colliding single protons, researchers collide heavy atomic nuclei such as gold nuclei or lead nuclei at enormous energies. For an instant, the collision region becomes hot enough and dense enough for a droplet of quark-gluon plasma to form. The relativistic heavy ion collider at Brookhaven National Laboratory has been central to this research. It has collided heavy ions, especially gold nuclei, to study the behaviour of nuclear matter at extreme temperatures and densities. The Large Hadron Collider at the European Organisation for Nuclear Research also studies quark-gluon plasma, especially through high-energy lead-ion collisions. The temperatures involved are astonishing. These tiny droplets can reach trillions of degrees, far hotter than the centre of the Sun. Of course, the droplets are also incredibly small and incredibly short-lived. They do not sit around politely while someone fetches a thermometer. They expand, cool, and transform into ordinary hadrons almost immediately. Detectors then study the particles that emerge. Collaborations such as STAR and Phoenix at the relativistic heavy ion collider, and ALICE, ATLAS, and CMS at the Large Hadron Collider have investigated the evidence for quark-gluon plasma. One of the most surprising results is that this plasma can behave like an almost perfect fluid in some conditions. That means it flows with extremely low internal resistance, rather than behaving like a simple gas of independent particles. This was not quite what many physicists first expected. The phrase plasma may suggest something thin and ghostly, but quark-gluon plasma can behave as a strongly interacting liquid. The quarks and gluons are not freely drifting around like people politely avoiding each other at a quiet library. They are interacting intensely, moving collectively, and producing flow patterns that detectors can measure. One important signal is called jet quenching. When a high-energy quark or gluon passes through quark-gluon plasma, it can lose energy to the medium. The resulting jets are altered compared with what would be expected in simpler collisions. This helps physicists study how dense the plasma is and how strongly it interacts with colour-charged particles moving through it. All of this adds a subtle layer to confinement. In ordinary cold matter, quarks and gluons are confined inside hadrons. But at extreme temperature and density, the usual hadron boundaries can dissolve into a larger deconfined medium. Confinement is therefore connected to conditions. It depends on the state of the strong interaction, the temperature, the energy density, and the environment in which quarks and gluons exist. Still, even in quark-gluon plasma, the central rule has not been casually broken. The quarks are not isolated as permanent free particles. They exist within a collective colour-charged medium, and as the plasma cools, they hadronize. Once again, colour-neutral hadrons emerge. This makes quark-gluon plasma one of the most beautiful exceptions that proves the deeper pattern. It shows that confinement has a history, a temperature, and a phase structure. The early universe itself passed from a quark-gluon plasma into ordinary hadronic matter. The particle that can never exist alone may, under extreme conditions, move through a larger sea of colour. But when the sea cools, the old rule returns, and the quark is gathered back into matter. The simplest quark model gave physicists a beautifully clear starting point. Baryons were made from 3 quarks, mesons were made from 1 quark and 1 antiquark. This explained many of the particles in the particle zoo, including protons, neutrons, pions, kaons, and heavier unstable hadrons. It turned a crowded catalogue into something closer to a recipe book, although admittedly one where the recipes involve unstable particles, and no one gets a relaxing dinner at the end. But quantum chromodynamics is richer than the simplest quark model. The most important rule is not that hadrons must always contain exactly 3 quarks, or exactly 1 quark and 1 antiquark. The deeper rule is colour neutrality. Observable hadrons must be colour neutral overall. If quarks and antiquarks can combine in a way that hides their colour charge, then quantum chromodynamics may allow more complicated structures. This possibility was present from the early days. Murray Gell-Mann, who helped create the quark model in 1964, recognised that more elaborate combinations might be possible. The early model focused mainly on baryons and mesons because those were the clearest and most established patterns. But the theory itself did not forbid every larger arrangement. It required the colours to balance. That opens the door to exotic hadrons. An exotic hadron is a hadron whose internal structure goes beyond the ordinary 3-quark baryon or quark-antiquark meson picture. 2 important examples are tetraquarks and pentaquarks. A tetraquark contains 4 quark-related constituents, usually described as 2 quarks and 2 antiquarks. A pentaquark contains 5, usually described as 4 quarks and 1 antiquark. These names sound almost playful, but they refer to serious objects in hadron spectroscopy. Hadron spectroscopy is the study of the masses, lifetimes, decay patterns, and internal structures of hadrons. It is one of the main ways physicists test quantum chromodynamics in the messy, strongly interacting regime where quarks are confined. For a long time, exotic hadrons were difficult to confirm. Particle physics is full of short-lived resonances, overlapping signals, and complicated decay chains. A bump in the data is not automatically a new particle. It might be a statistical fluctuation, a conventional hadron behaving unexpectedly, or a complicated interaction between known particles. Physicists have to be careful, because the subatomic world does not label its surprises very neatly. In recent decades, however, evidence for exotic hadrons has become much stronger. The LHCb collaboration at the Large Hadron Collider has been especially important in this area. LHCb was designed to study particles containing bottom and charm quarks, and it has made major contributions to the discovery and investigation of exotic hadron candidates. In 2015, LHCb reported evidence for pentaquark states in decays of a baryon containing a bottom quark. Later studies refined and expanded the picture. Other experiments, including Bell, Bassi, and earlier Collider collaborations, have also contributed to the study of tetraquark and exotic meson candidates. These discoveries show that quarks can gather in more ways than the earlier simple model suggested. But they do not break confinement. A tetraquark is not a free quark. A pentaquark is not a loose quark escaping into open space. These particles are still composite hadrons. They are still colour neutral overall. Their quarks and antiquarks are still bound by the strong interaction. They may be arranged as tightly bound multiquark states, or in some cases as looser hadronic molecules, where 2 colour-neutral hadrons are bound together in a way somewhat reminiscent of atoms forming a molecule. The exact internal structure can differ from state to state, and this is part of what makes exotic hadrons so interesting. The strong interaction is flexible. It can bind 3 quarks into a proton. It can bind a quark and antiquark into a pion. It can allow more complicated combinations that briefly appear in high-energy experiments and then decay into lighter particles. The rules are strict, but not simple in the everyday sense. They are more like the rules of a deep grammar. Many sentences are possible, but not every random arrangement of words is allowed. That is a helpful way to think about exotic hadrons. Quarks are the letters. Ordinary baryons and mesons are the most common words. Exotic hadrons are longer, rarer, more complicated phrases. Some are fleeting, some are difficult to interpret, but all of them still obey the grammar of colour neutrality. This makes them valuable tests of quantum chromodynamics. The more ways quarks can combine, the more physicists can study the strong force under different conditions. Each exotic hadron candidate gives clues about how quarks and gluons behave when simple approximations fail. It helps reveal whether quantum chromodynamics can explain not only the familiar particles of ordinary matter, but also the stranger-bound states that appear at the edge of modern experiments. And the lesson returns to the same quiet rule. Quarks can gather in surprising families. They can form protons and neutrons. They can appear in mesons, tetraquarks, pentaquarks, and other possible color-neutral arrangements. They can build stable matter, short-lived resonances, and particles that exist only briefly inside detector data. But the individual quark does not step out alone. Even in the exotic cases, confinement remains. The quark may join larger and stranger households, but it never becomes a solitary traveller. Nature allows variety, complexity, and unexpected combinations, while still keeping colour charge hidden. The particle that can never exist alone can belong to more structures than physicists first imagined, but it must always belong to something. The story of quarks begins inside the proton, but it does not stay there. The same strong interaction that shapes the smallest stable pieces of atomic nuclei may also matter inside some of the densest objects in the universe. These objects are neutron stars, collapsed stellar remnants left behind when massive stars explode as supernovae and their cores are squeezed into something almost beyond ordinary imagination. A neutron star can contain more mass than the Sun, compressed into a sphere only about the size of a city. Its density is so extreme that a single teaspoon of neutron star material is often described as having a mass comparable to a mountain. This comparison is not exact in every detail, because neutron star matter cannot simply be scooped up and placed politely beside the sugar, but it gives the right feeling. The matter is crushed to a degree that everyday experience cannot prepare us for. The path toward understanding such objects began long before neutron stars were observed directly. Subramanian Chandrasekhar showed that there is a maximum mass for a white dwarf star, beyond which electron degeneracy pressure cannot hold it up against gravity. Lev Landau thought deeply about dense stellar matter and the possibility of stars made largely of neutrons. In the 1960s, Jocelyn Bell Burnell and Anthony Hewish discovered pulsars, which were soon understood as rapidly rotating neutron stars emitting beams of radiation. The discovery turned neutron stars from theoretical possibilities into real astronomical objects. Inside a neutron star, matter is packed so tightly that atoms cannot survive as atoms. Electrons and protons are forced together under enormous pressure, producing neutron-rich matter. Near the outer regions, there may be a crust of atomic nuclei and free electrons. Deeper in, the material becomes stranger, mostly neutrons, some protons, electrons, and possibly more exotic forms of matter depending on the density. And at the deepest levels, physicists ask an extraordinary question. Could the pressure become so intense that neutrons themselves begin to lose their separate identities? Could matter transition into a state involving deconfined quarks, where quarks are no longer confined inside individual protons and neutrons in the ordinary way? Could strange quark matter exist in the cores of some neutron stars, involving up, down, and strange quarks in a dense collective state? These are not settled answers. They are active research questions. The interior of a neutron star cannot be opened and inspected. No telescope can simply look down into the core and see whether the matter is made of neutrons, hyperons, deconfined quarks, or something even more subtle. Physicists have to infer the internal structure from mass, radius, rotation, cooling behaviour, magnetic fields, and the way neutron stars behave when they collide. Modern observations have made this field far richer. The Laser Interferometer, Gravitational Wave Observatory and Virgo have detected gravitational waves from neutron star mergers. These events send ripples through space-time as two neutron stars spiral together and collide. The shape of the gravitational wave signal carries information about how easily the stars deform under each other's gravity. That deformability depends on the internal stiffness of neutron star matter. This stiffness is described by what physicists call the equation of state. In spoken terms, it is the relationship between pressure, density, and energy inside the star. A softer equation of state allows matter to compress more easily. A stiffer one resists compression more strongly. Different possible forms of dense matter, including possible quark matter, would affect the maximum mass, radius, and merger behavior of neutron stars. This is where confinement reaches up into astrophysics. In ordinary matter, quarks are confined inside protons and neutrons. But under the enormous pressure inside a neutron star core, the usual hadron picture may change. The boundaries between individual neutrons might become less meaningful. Quarks might move through a denser, more collective medium, or confinement may remain dominant, keeping the matter mostly in hadronic form even under extreme conditions. The truth may depend on the star. Some neutron stars may be dense enough to contain exotic phases in their cores. Others may not. There may be gradual transitions, mixed phases, or sharp changes from one form of matter to another. The problem is difficult because it involves gravity, nuclear physics, quantum chromodynamics, and observations of objects thousands or millions of light years away. It is, in other words, exactly the kind of situation where the universe appears to have set an exam and then hidden most of the paper. But the question itself is beautiful. The strong interaction is not only a force inside accelerators. It is not only a theory used to explain jets, hadrons, and the mass of the proton. It may help determine the fate and structure of collapsed stars. The behavior of quarks under pressure may decide how large a neutron star can be before it collapses further into a black hole. It may shape the gravitational waves we detect on Earth. So the particle that can never exist alone belongs to a story that stretches from the heart of the atom to the remains of dead stars. The same confinement that hides quarks inside protons may also influence the densest matter we can observe in the cosmos. Deep inside a neutron star, under pressure beyond anything found on Earth, nature may be testing how far that hidden rule can bend before matter becomes something new. There is a quiet kind of mystery left at the bottom of this story. It is not the kind that says physicists have no idea what is happening. That would be much too dramatic and also not true. Quantum chromodynamics is one of the most successful theories in modern physics. It explains quarks, gluons, color charge, asymptotic freedom, jets, hadron structure, and a vast amount of experimental data from particle accelerators. It is built into the Standard Model, tested across decades, and supported by both experiment and computation. And yet, one of its deepest features remains mathematically unfinished. That feature is confinement. Physicists know, from every direct search and every relevant experiment, that free isolated quarks have not been observed. They know that high-energy collisions produce jets of hadrons rather than lone quarks. They know that lattice quantum chromodynamics strongly supports a world where color-charged particles are bound into color-neutral combinations. They know that the theory works with extraordinary accuracy in many regimes. But a complete rigorous proof of confinement from the first principles of quantum chromodynamics remains beyond current mathematics. This is where physics and mathematics meet in a very deep way. Quantum chromodynamics is a type of theory known as a non-abelian gauge theory. The mathematical foundations of this kind of theory trace back to Chen-Ning Yang and Robert Mills, who introduced Yang-Mills theory in 1954. Their work was not originally built specifically for the strong interaction, but it became foundational for the modern understanding of particle physics. The strong force, as described by quantum chromodynamics, is a Yang-Mills theory with color charge. The phrase non-abelian sounds rather formal, but the central idea can be said gently. In some theories, the order of certain operations does not matter. In others, the order does matter. Non-abelian gauge theories belong to the second kind. Their fields have a richer internal structure, and that richness allows the force-carrying particles to interact with one another. This is exactly what happens with gluons. In electromagnetism, the photon does not carry electric charge, so photons do not normally interact directly with other photons. The electromagnetic field is mathematically simpler in this respect. In quantum chromodynamics, gluons carry color charge, so gluons interact with other gluons. The field is not just a background messenger system, it is self-interacting. It ties itself into the behavior of the force. This self-interaction is part of what makes the strong interaction so powerful and so difficult. At short distances, quantum chromodynamics becomes easier to handle because of asymptotic freedom. Quarks interact more weakly when they are extremely close together or probed at very high energy. In that regime, physicists can use approximation methods with great success. But confinement belongs to the long-distance, low-energy regime where the strong coupling becomes large. There, the ordinary methods become much harder to use. This is one reason confinement remains mathematically subtle. The Clay Mathematics Institute includes the Yang-Mills existence and mass gap problem among its Millennium Prize problems. This problem asks, in broad terms, for a rigorous mathematical construction of quantum Yang-Mills theory and an explanation of why it has a mass gap. A mass gap means that the lowest possible excitation above the vacuum has a positive non-zero mass. In the context of the strong interaction, this is connected to why the force does not produce freely travelling massless gluons in the ordinary way, and why the observed particle spectrum begins with massive colour-neutral states. This is not merely a technical footnote, it touches the deepest structure of quantum field theory. Quantum chromodynamics works, it predicts, it organises, it explains, it helps physicists understand why protons and neutrons exist, why jets form, why quarks behave almost freely at short distances, and why they never emerge alone. But turning all of that into a perfectly rigorous mathematical proof is another level of challenge. This should not be mistaken for weakness. Many areas of physics are supported by overwhelming evidence before every mathematical detail is placed on perfectly polished foundations. Confinement is not a guess waiting nervously in the corner. It is a deeply supported feature of the strong interaction, confirmed indirectly in countless ways. No detector has seen a free quark. High-energy experiments show hadronization. Lattice calculations reproduce hadron behavior. The Standard Model's description of quarks and gluons is extraordinarily successful. The open problem is not whether physicists randomly invented confinement to cover embarrassment. It is whether the complete mathematical machinery can be built from the ground up with full rigour. The physical picture is strong. The formal proof is still being refined. There is something rather beautiful about that. At the smallest scales of ordinary matter, we find a rule so reliable that every atom depends on it, and yet so mathematically deep that it remains one of the great unfinished tasks of theoretical physics. The quark is real, experimentally necessary, and central to the structure of matter. It explains the proton, it helps build the neutron, it gives order to the hadrons, it shapes much of the mass of the visible world, but it is still bound by a rule that keeps it hidden from isolation. The particle that can never exist alone stands at an unusual boundary. It is not speculative in the casual sense. It is not imaginary. It is one of the best supported ingredients of modern particle physics. And still, the full proof of why it must always remain confined reaches into some of the deepest mathematics we know. So the story ends its final turn with a fitting kind of balance. The quark is discovered but never held alone. The theory is powerful but not mathematically finished. The evidence is overwhelming, but the foundations remain profound. Matter is stable but not simple. And inside every quiet atom, a hidden rule continues to do its work. The particle that can never exist alone is the quark, not because it is imaginary, not because it is merely a symbol in an equation, not because physicists invented it to make the diagrams look tidy and then quietly hoped no one would ask too many follow-up questions. The quark is one of the fundamental ingredients of the standard model of particle physics. It is essential to the structure of protons and neutrons. It explains the pattern of hadrons. It appears in the evidence from high-energy scattering, particle jets, accelerator experiments, and the behaviour of matter itself. And yet, as far as every experiment has shown, a quark cannot be isolated as a free particle. The reason is confinement. Quarks carry colour charge, the special kind of charge involved in the strong interaction. The strong interaction is described by quantum chromodynamics, the theory of quarks, gluons, and colour fields. In the world we observe directly, particles with exposed colour charge do not appear alone. Instead, quarks and gluons are confined inside colour-neutral matter. A proton hides the colour charge of 3 quarks in a balanced combination. A neutron does the same. A meson balances the colour of a quark with the anticolour of an antiquark. More exotic hadrons can contain more complicated arrangements, but the same rule remains. The final particle must be colour-neutral overall, so the quark is not absent from reality. It is hidden inside the structures that reality allows. The journey began with ordinary matter, the calm surfaces of tables, walls, cups, hands, and stars. Matter seemed solid and continuous, but the atomic theory of John Dalton showed that it could be understood as built from atoms. J.J. Thomson's discovery of the electron in 1897 revealed that atoms were not indivisible. Ernest Rutherford's gold foil experiment, interpreted in 1911, revealed the tiny dense nucleus at the atom's centre. James Chadwick's discovery of the neutron in 1932 helped complete the early picture of nuclear structure. But the nucleus created a problem of its own. Protons are positively charged, and according to the electromagnetic force described by Coulomb's law, they should repel one another. The nucleus should not be so calm. Something stronger had to bind protons and neutrons together at very short distances. Hideki Yukawa's idea of force-carrying mesons offered an early way to understand the nuclear force, pointing toward the deeper particle physics that would follow. Then the particle zoo arrived. Cosmic ray studies, cloud chambers, bubble chambers, and accelerator experiments revealed more and more short-lived particles. Carl Anderson discovered the positron in 1932, opening the real experimental story of antimatter. Mesons, baryons, strange particles, and unstable resonances began to fill the records of institutions such as Brookhaven National Laboratory, Lawrence Berkeley National Laboratory, and the European Organisation for Nuclear Research. The list grew so long that it began to look less like a final catalogue of fundamental objects and more like a sign of hidden order. Murray Gell-Mann and Yuval Ne'eman helped reveal that order through the Eightfold Way, arranging hadrons according to properties such as electric charge, strangeness, and mass. The successful prediction and discovery of the Omega- baryon at Brookhaven National Laboratory in 1964 showed that the pattern was not just a tidy filing system. It was pointing towards something deeper. That deeper idea became the quark model. In 1964, Murray Gell-Mann and George Zweig independently proposed that hadrons were built from more fundamental constituents. Gell-Mann called them quarks. Zweig called them aces. The name quark remained. The first 3 flavours were up, down, and strange. Later came charm, bottom, and top. Protons and neutrons could now be understood as combinations of up and down quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Mesons could be understood as quark and antiquark combinations, while baryons were built from 3 quarks in the ordinary model. At first there was hesitation. Quarks carried fractional electric charges, such as positive 2/3 or negative 1/3 of the proton's charge. No one had seen such charges isolated in nature. but deep inelastic scattering at the Stanford Linear Accelerator Center in the late 1960s changed the confidence level. Jerome Friedman, Henry Kendall, and Richard Taylor helped reveal point-like constituents inside protons. Richard Feynman's parton model described these internal objects before they were fully understood as quarks and gluons. The proton was not smooth. It had an interior. Then color charge explained why quarks could exist inside hadrons but not appear alone. Oscar Greenberg, Yoichiro Nambu, Mu-Young Han, Harold Fritsch and others helped develop the ideas that led toward quantum chromodynamics. Color charge solved problems involving the Pauli exclusion principle and particles such as the omega-minus baryon. It also gave the strong interaction its defining rule. Observable hadrons must be color neutral. Gluons deepened the picture further. They are the force carriers of the strong interaction, but unlike photons in electromagnetism, gluons carry the very charge they respond to. They interact with other gluons. The messenger also feels the force. This self-interacting gluon field helps explain why the strong interaction behaves so differently from familiar forces. David Gross, Frank Wilczek and David Politzer showed in 1973 that quantum chromodynamics has asymptotic freedom. At extremely short distances, quarks interact more weakly and can behave almost like free particles inside a hadron. This explained why deep inelastic scattering saw point-like partons inside the proton. But this was not ordinary freedom. When quarks are pulled farther apart, the strong interaction does not simply fade away. Energy builds in the color field. This is confinement in its clearest form. The color field can be pictured as a flux tube between quarks. Pulling quarks apart stores energy in that tube. Eventually, the energy becomes enough to create a new quark and antiquark pair. The field breaks, but not by releasing a lone quark. It breaks by forming new color-neutral hadrons. Every attempt to separate a quark produces more bound matter instead of an isolated quark. This is why particle detectors see jets, electron and positron collisions at the German electron synchrotron, and other accelerators revealed sprays of particles that carry the fingerprints of quarks and gluons. The Tasso collaboration's observation of three jet events in 1979 gave strong evidence for gluon radiation. But the detector still did not see a bare quark or a bare gluon. It saw hadronization, the transformation of energetic color-charged objects into streams of color-neutral particles. The story widened through the 6 flavors of quark, from the ordinary up and down quarks inside protons and neutrons to the heavier strange, charm, bottom, and top quarks created in high-energy environments. It widened again through the proton's mass, most of which does not come from the bare masses of its valence quarks, but from quark motion, gluon fields, C-quarks, antiquarks, and the energy of quantum chromodynamics. Einstein's mass-energy relation reminds us that mass and energy are equivalent, and energy divided by the speed of light squared contributes to mass. Much of the weight of ordinary matter comes from the confined energy of the strong force. Lattice quantum chromodynamics, developed from the work of Kenneth Wilson and lattice gauge theory, gave physicists a way to study this force with supercomputers. By placing quantum chromodynamics onto a grid of space-time points, researchers can calculate hadron properties in regimes where simple approximation methods fail. These calculations strongly support confinement and reproduce many features of the hadrons observed in experiment. Quark-gluon plasma showed that confinement also has a relationship with extreme conditions. At the relativistic heavy ion collider and the Large Hadron Collider, heavy ion collisions can create tiny droplets of matter, where quarks and gluons are not confined inside individual protons and neutrons in the ordinary way. The early universe itself likely passed through such a state before cooling into ordinary hadronic matter. But even this is not a jar of lonely quarks. It is a collective hot medium, and as it cools, color-neutral hadrons return. Exotic hadrons showed that quarks can gather in more ways than the simplest model first suggested. Tetraquarks and pentaquarks, studied by experiments including the LHCb collaboration at the Large Hadron Collider, reveal the flexibility of the strong interaction. But they do not break confinement. They are still color-neutral combinations. The individual quark still does not step out alone. Even neutron stars carry the question into the sky. In the densest stellar remnants, where matter is compressed beyond ordinary nuclear density, physicists ask whether quark matter or strange quark matter might exist deep inside. Observations from the Laser Interferometer, Gravitational Wave Observatory, Virgo and neutron star merger studies help constrain these possibilities. The answer remains uncertain, because neutron star cores cannot be inspected directly. But the same strong interaction that shapes protons may also help decide the structure of some of the densest objects in the universe. And beneath all of this remains the unfinished proof. Quantum chromodynamics is extraordinarily successful. Confinement is supported by experiment, by computation, by jets, by hadron spectroscopy, by the absence of free quarks, and by the whole structure of the Standard Model. But complete rigorous mathematical proof of confinement from first principles remains an open challenge. The Yang-Mills existence and mass gap problem, one of the Clay Mathematics Institute Millennium Prize problems, connects this physical fact to the deepest mathematics of quantum field theory. Chen-Ning Yang and Robert Mills introduced the kind of non-abelian gauge theory that became foundational to the modern description of the strong interaction. The theory works. The evidence is overwhelming. The final proof is still being refined. So the mystery is not that physicists do not know whether quarks matter. They do. The uncertainty is more subtle and more beautiful. Confinement is not a wild guess. It is a deeply supported feature of nature whose complete mathematical foundation remains one of the great unfinished tasks of modern physics. The quark is real, fundamental, and hidden. It helps build protons and neutrons. It gives order to the particle zoo. It explains the patterns of hadrons. It leaves fingerprints in jets. It contributes to the mass of ordinary matter. It may even play a role inside the cores of neutron stars. But it never appears alone. And that is the calm final image of the story. Every ordinary object around us is held together by rules far beneath sight. The table, the wall, the air, the body, the stars, and the quiet room are all made possible by particles that belong to matter without ever standing apart from it. Inside the proton, the deepest pieces are not tiny loose beads waiting to be removed. They are bound by colour, shaped by gluons, and gathered by the strong interaction into the stable structures of the world. Ordinary matter is quiet, not because it is simple, but because its hidden rules are so powerful. The particle that can never exist alone is one of the reasons anything can exist together.